These are the practice problems for lesson 2, graphs of proportional relationships. This is problem number 1. In this problem, they ask you to graph the relationship between the distance a tortoise runs compared to the distance the hare runs. So this is a race between the tortoise and the hare. And they give you the equation. The equation is y equals 4x. So x is the distance that the tortoise runs in miles, and y is the distance that the hare runs in miles. So when you look at a problem like this, and you could easily graph, if you plug in for x a value of 4, that's going to give you y a value of 16. So let's go over to 4 and go up to 16, place a point there, and you can graph this. So that would be pretty easy. But when you look at problems like this, where you're at and learning about proportional relationships, graphs, slopes, all that stuff, run these ideas through your head. You don't have to write it down, but at least try to think through it. So for example, what does this 4 mean right here? Well, this is the slope. It means that for every measure along the y-axis, every vertical measure, that is 4 times the measure along the horizontal axis. So this is 4 units or 4 miles for every 1 unit or 1 mile that the tortoise moves. So this measure right here, the vertical measure, is 4 times the horizontal measure. So 4 times 1 is 4. So we zoom in on this a little bit. That's called the unit rate. So in 1 mile, 1 unit that the tortoise moves, how far does the hare or the rabbit move? Well, the hare moves 4 miles. So the hare's miles per 1 tortoise mile is called the unit rate. So once again, the vertical measure is 4 and the horizontal measure is 1. So the vertical measure is 4 times the horizontal measure. That is the slope. And when you look at just a single unit along the x-axis, that becomes the unit. So that 1 is the unit rate. So what's the rate that the hare is moving compared to the tortoise? Is 4 times what the tortoise is moving. So the slope is 4. So for every vertical measure, so this would be 8 units, that's 4 times the horizontal measure, 2. Well, 4 times 2 is 8. So if you use the x value as 2, 2 times 4 is equal to 8, because the y, the measure in the vertical direction, the hare's distance, is 4 times what the tortoise moves. So it's 4 times 2 equals 8. So just run this stuff through your head. Now notice that this is a little bit easier because this goes through 0, 0. So you don't have to subtract anything or add anything. It's just that the y coordinate is the vertical measure. It's 4 units. So it's 4 minus 0 is 4. So you just have to write down the y coordinate, and the x coordinate is the horizontal measure. It's just 1 minus 0 is 1. And so that ratio, 4 to 1 is 4, so it gives you a slope of 4. So proportional relationships, writing equations and slopes, a little bit easier because you just have to look at the coordinates and write that as the ratio, that's the slope. And also it's the left side of the equation. It's y to x, or y over x, is equal to 4. And that tells you that the vertical measure is 4 times the horizontal measure. So then you can rewrite that in this form, y equals 4x. So you're getting there. Y is 4 times the value of x. So the hare is running 4 times farther than what the tortoise runs for each mile that whatever the tortoise runs, the hare runs 4 times farther. So whatever this value of x is, 3, 4, 5, let's use 5 for a second. 4 times 5 is 20. So if the tortoise runs 5 miles, the hare will have run 20 miles, 4 times farther. So if the tortoise runs 2 miles, the hare will have run 8 miles, 4 times farther. So the 8 hare miles for every 2 tortoise miles, or 4 hare miles for every 1 tortoise miles. So you go out here to 4. 4 times 4 is 16. So the tortoise runs 4 miles, the hare runs 4 times farther. So y equals 4x. So the vertical measure is 4 times the horizontal measure. The horizontal measure in this case is 4 miles. That means the vertical measure in this case, no, the horizontal measure in this case is 4 miles. That means that the hare will have run 16 miles. So the vertical measure is 4 times the horizontal measure. Y is equal to 4 times whatever the value of x is. It takes a while to get used to. That's why I'm asking you to just run this stuff. Just run it all through your head. You don't have to write it all down. If you write it down and practice writing it down, it will stick that much better in your head. You'll start to understand it that much better. You're going to have to work at it. This is practice problem number 1 for lesson 2. This is problem number 2. In problem number 2, there is a scale that's a spring scale. And as you add weight to that spring scale, that spring stretches out. And so you can measure the length that spring stretches in centimeters. And the weight is measured in something called newtons. And we're not going to go into what a newton is. It's just a measurement of weight. All you have to know is that it is proportional to the distance that spring stretches. This is a proportional relationship. If there's no weight on the scale, then that spring will stretch 0 distance, 0 centimeters. So it's a proportional relationship that goes through 0. And you're supposed to fill in the rest of this table based on that information. So first of all, what is the relationship of the weight that's on the scale to the distance that the spring stretches? That is the slope. That is the what we call the constant of proportionality. So the measurement in the vertical distance on a graph, or the y, along the y-axis, is going to be a ratio to the measurement in the horizontal distance along the x-axis. That's going to be the slope, or the constant of proportionality. So that ratio gives you the slope. So y over x, the measurement of y over x. Now, because it's a proportional relationship, you can use the value of y and you can use the value of x. Because if you remember back, and I'm going to show you this in a little bit, if you remember back to the slope triangle, it's already at 0, 0. You don't have to add anything or subtract anything. It's already at that point. So the y coordinate is the vertical measurement, the number of vertical units, and the x coordinate is the horizontal measurement, or the number of horizontal units. That ratio is the slope. In this case, it's 28 units in the y direction along the y-axis and 20 units in the horizontal direction along the x-axis. That ratio simplifies to 7/5. 28 divided by 4 is 7, and 20 divided by 4 is 5. So the length along the y-axis is 7/5 the length along the x-axis. 7/5 times this x value will give you the y value. So the measurement in the vertical distance, or the vertical direction, is 7/5 the horizontal measurement. So you can multiply then the value along the x-axis, the x value, by 7/5, and that will give you the y value, because the y value is 7/5 of that x value. So 55 times 7/5 is 7 times 55/5. So you can simplify this part to 11. And so then 7 times 11 is 77. So if the spring stretches 55 centimeters, then you will have put 77 newtons of weight on the scale. Now, in this case, they give you 140 as the number of newtons, and they want you to calculate the centimeters that the spring stretches. Now, that is the opposite, the reciprocal relationship. Let's get a graph here. I'm going to move to here because it's a little bit easier to explain. So the vertical, along the y-axis, the vertical direction is 7/5 of the horizontal direction, the horizontal measurement. So this 7 is 7/5 of 5. But if you want to measure, if you want to calculate the horizontal measurement, that is 5/7 of this vertical measurement. So this length right here is 5/7. So 5 is 5/7 of 7. So just think of something divided into 7 equal parts. This in this direction is 5 of those. If you are calculating this direction, think of the horizontal direction divided into 5 equal parts, and you want 7 of those 5 equal parts. So this is 7/5. This is 5/7. So if you know the vertical direction, the number of units in the vertical measurement, the horizontal measurement, or the x value, is 5/7 of that y value. So 5/7 of 140 is 140 divided by 7 is 20, because 14 divided by 7 is 2. 140 divided by 7 is 20. 5 times 20 is 100. So think about 100 divided into 5 equal parts. That's 20 for each of those parts. 140 is 7 of those parts. Think of 140 divided into 7 equal parts. Each part is 20. 100 is 5 of those parts. So you just have to go back and forth. Eventually, it will make sense to you. For 1 centimeter stretch, the weight equals 7/5 newtons. So this is the unit rate down here. So for 1 unit of distance, 1 centimeter, how much weight goes on to the scale? 7/5 newtons, or 1 2/5 newtons. That is called the unit rate, because it's the amount for 1 unit along the x-axis. So you go 1 unit along the x-axis, this value along the y-axis is going to be 7/5 centimeters. 7/5 units, or 1 2/5 centimeters. And then you're supposed to state what scales you would set up to get all of this data on one graph. Well, notice that the farthest it goes out along the y-axis is 140 newtons. So it goes up to 140 newtons, and the farthest it goes on along the x-axis is the x value that corresponds to that 140 newtons, which is 100 centimeters. So you want to set up a graph that would go to the right 100 centimeters. So you'd set up your scale to mark it out 100 centimeters, and to go along the y-axis, you would mark the scale to go up 140 newtons along the y scale. This is the unit rate right here. So 1 centimeter gets you to 7/5 newtons. So it's 1 2/5 newtons, which is 7/5 newtons. Go back to here just for a second. So we're starting to look at this equation often now. So y equals kx. So the value of y is the slope times the value of x. So in this case, that slope is 7/5. So that is called the constant of proportionality. So it's 7/5, whatever the value of x is equal to y. So you're going to get used to this as you look at it and think about it. All right, so this is problem number 2. Okay, this is problem number 3. What you're supposed to do is show that this smaller image is a scale copy of this larger image through a series of transformations, either translation, reflection, rotation, or several of those, and a dilation. That will prove that this smaller image is a scaled copy of this larger image. Now, this took me a little while to figure out or to realize that this is a reflection. So if I can bring this image, scale it down to the size of this image, and then reflect it over a line of reflection, then I can match this image. And what really gave me that clue is looking at DC. So segment D double prime to C double prime, and segment D to C. And so then I started to think, well, I need to get point D down here to match across from point D double prime. So how can I get it to this circle right here? And that is using a scale factor of 1/3. So if I use a scale factor of 1/3 and use the center of dilation, point A, that's going to bring D to this point right here. Then I have to find a line of reflection that's midway between these 2 points. Well, if I can just count this way, 1, 2, 3, 4, right here, and then count this way, 1, 2, 3, 4, it gets me at this line right here. So I'm going to show you that. But that's my initial thinking of, gee, how should I do this? How should I go about this? All right, so it was to dilate this using a scale factor of 1/3, so you're going to bring it closer to the center of dilation, closer to point A. So D is going to go to here, scale factor of 1/3. So this is 1/3, 2/3, 3/3. And then I'm going to reflect it from that point directly across here. So that line of reflection has to allow me to move this point in a perpendicular direction, and it's going to be, the line of reflection is midway in between. So I'm going to move it to the line of reflection, and then an equal distance past that line of reflection on the other side. All right, so here's the scale using the scale factor of 1/3. So the dilation brings D to point A. The scale factor of 1/3, that dilation brings point C to C prime right here. So this is 1/3, this is 2/3, this is 3/3. So now I can connect these 2 points, D prime to C prime, and I can reflect them over this line of reflection to right here, D double prime, C double prime. So this gets kind of messy. Lots of lines, all these circles, and then these 2 images, and then how are you going? How are you moving from one place to another, the line of reflection? You just have to kind of try to keep track of it. B is scaled 1/3. So from point A, that's the center of dilation. 1/3 of this distance is the distance right here. So this is 1/3, 2/3, 3/3. So every 3 circles is a third in this case. That brings point B prime to right here. If I connect those 2 points, then I can dilate them across this line of reflection. Same line of reflection. It has to be the same line of reflection to get to B double prime. And finally, E, I can dilate using a scale factor of 1/3 to this point right here. And so this is 1/3. So 2 lines is 1/3 in this case, or 2 circles. 1/3, 2/3, 3/3. So that gets me to right here. And so now if I connect B prime to E prime, then I can reflect that over this line of reflection. So that's going to go right here. So point E double prime is going to go right here. And then I connect it to B double prime. And finally, I can finish it by reflecting this last line segment. Actually, it's already reflected. You just have to connect the points to complete the quadrilateral. All right, so lots of stuff. Now, if I add the reflections with this lighter blue color, so D prime is going to D double prime, C prime is going to C double prime, B prime is going to B double prime, and E prime is going to E double prime. Each of those is moving in a perpendicular direction to the line of reflection and an equal distance across that line of reflection to the other side. Then you just connect the points and you have the scaled copy, the reflected image of this larger image. And if I get rid of all that and just label, this is the dilation going from this image to this image, and then this is the reflection going from the red image to the orange image. A little bit easier to look at. See how I did that. All right, so this is problem number 3. This is problem number 4, and for problem number 4 you have 2 statements. One is that congruent figures cannot be similar, and the other statement is congruent figures are similar with a scale factor equal to 1. So number 1 is actually false. Congruent figures are similar with a scale factor equal to 1. So congruent figures are always similar to each other. It's just that they're not made larger or they're not made smaller. It's just an exact copy with the scale, and that means the scale factor is 1. So that's number 2. Congruent figures are similar with scale factor equal to 1. So that is true. So if I take this figure and if I make an identical copy of it and I just rotate it a little bit, so it's still a congruent figure and it still has a scale factor of 1. Because if you think about the center of dilation being one of the vertices, then this length is going to be the unit length that you deal with for that dilation, and it's that length times 1 gives you that length. So a scale factor of 1 just makes a copy of that length. This length right here would be the length for this, the scale from the scale at this point, and it just scales it onto itself. So that would be a scale factor of 1. All right, so number 2 is true. Congruent figures are similar with scale factor of 1. And number 1 is false. Congruent figures cannot be similar. Actually, congruent figures are always similar, again, with a scale factor of 1.